Alright folks, starting chapter 7 here. It's analytical trigonometry, so this is a lot of the identity stuff. There's going to be a lot of algebra here that we are going to work with. That might seem a little abstract, but whenever we get stuck, we'll go back to substitution and using like little examples of what would I do in this case if we had numbers in these certain positions instead of trig ratios. Think about the algebra that'd be involved with that, and then conduct that exact same algebra on the trig ratios. Okay, so we'll walk through a couple examples of that here in a little bit. But it's trigonometric identities. Remember what an identity is. Identity is an algebraic equation in which provides a true statement regardless of the input value. Meaning that this is probably one of the most basic identities you've ever seen. One of the first ones we ever came across. No matter what I do, no matter what I put in for x here and put in for x there, the left-hand side is going to equal the right-hand side. This statement is always true regardless of what you plug in for x. Okay. Same thing here. This is one of your identities, and this identity here is based off, and a lot of your formulas from algebra that you learned, like a plus b squared turns into a squared plus 2ab's plus b squared. That's an identity no matter what a and b are. This here is always equal to that. You had some with like a plus b cubed. Okay, well that became a plus b a squared minus 2ab plus b squared. If you remember a sum of a cube of sums or a cube of differences, you had those formulas. So these are all identities. No matter what I plug in, sorry about that. No matter what I plug in, the left-hand side is going to be identical to the right-hand side. The number one trig identity that we have seen already in chapter 5 and 6 is that guy right there. Sine squared x plus cosine squared x equals 1. No matter what you do there, whatever you put in for x, add these together, you're always going to get 1. Okay. So trigonometric identity is an identity that incorporates one or more trig functions. And these are your basics, okay? And they should look familiar, okay? We've got our reciprocal functions, secant, cosecant, cotangent, tangent, and cotangent. We've got our Pythagorean identities, okay? Sine squared plus cosine squared equals 1. Remember, that thing is what generates these. If I divide everything here by sine squared, it generates that one. If I divide everything here by cosine squared, it generates that one. Now when I say it generates this one, after maybe recognizing that some of these happened. Okay. Here are even odd properties that we've talked about in the past. Spent a good amount of time in chapter 6 discussing these. And then we got our co-function identities, and we spent again a good deal in chapter 6 towards the end, recognizing the algebra that allowed for us to say that. Remember, this is 90 minus x, 90 degrees, if I want to talk about measurements that way. So sine and cosine, they pair up. Okay, cosine and sine, they pair up. Okay, in that order. Tangent, cotangent, they are obviously co-functions. They share the same root word, but one has the prefix co on it. And that co, if you remember, referred to the idea that that angle and that angle, if we add them together, we get pi over 2 or 90 degrees, so they're complementary. And the secant, cosecant. So those are co-function identities that we may incorporate. So here's the thing: if we're working on a problem and we see that, I hope we don't leave it that way. I hope what we do is we substitute it with cosine, because it's going to make things a little bit easier for us. Okay. So these are things that, guys, I know we've been talking about. We're going to use them over and over and over again. My hope is that at this point, maybe you haven't memorized them, but you understand them. You know where they come from. Okay, you understand the relationships that exist between them. So trigonometric identities allow us to rewrite the same expression in different ways, usually in an effort to make something appear simpler in algebraic form. In simplifying algebraic expressions, we use factoring, common denominators, and product formulas. The same will occur with trigonometric expressions. However, we'll also incorporate trigonometric identities as well. So this is going to be, this whole early on couple sections is going to be designed for us to be able to start eventually solving trigonometric equations. You might not recognize right away what we're doing and why we're doing it, but hopefully if you can kind of foreshadow, what if this thing was inside an equation, okay? We would have to combine like terms and reconfigure this thing so we can isolate a variable. So these examples that we work through are kind of small snippets of other problems that we're going to want to condense these, simplify them, so that when they show up in other problems, we can make those other problems easier to deal with. I know that sounds messy, confusing, but once you see a hang of this, hopefully with practice we'll be okay with this. All right, so when we simplify expressions, the number one thing to remember is if you get stuck, rewrite everything in terms of sine and cosine and then rely on your algebra skills, okay? My personal opinion, that's what I like to do. I'm more comfortable with my algebra than I am with recognizing a identity, okay, and doing substitution that way. The end game is to use a little bit of both. Use your algebra skills and substitution skills with identities, and it should maybe make the process a little bit easier. But in this first one, because we don't know what we're doing yet, and I haven't shown you any examples, what I want to do is I'm just going to make sure that every one of these things is written in terms of sine and cosine. So cosine obviously is written in terms of itself. Tangent is not, though. So I'm going to rewrite tangent. So I'm going to rewrite everything as cosine t plus, now tangent t in regards to sine and cosine is sine divided by cosine. And then I'll multiply by sine of t. Okay. So when we do that, what happens here? Well, we get cosine squared, cosine t plus, now, if I actually do this, so once I get everything in terms of sine and cosine, I actually go through my order of operations and combine like terms and that information, set of processes, and just try to rewrite things and simplify and combine like terms. So when I get this math here, it tells me I'm going to multiply. So what's that give me? It gives me sine squared t over cosine t. And this is what I mentioned earlier, is that when we get stuck, we don't know what to do, we put numbers in here and think about what would I do with something like this if this was a number. So let's say, so cosine is a number between -1 and 1. So let's just say it's, I don't know, 1/2. And I add to that, okay, so sine squared, so maybe that's 1/4. I don't know, it's a fraction between -1 and 1. Again, that's what sine is. But I squared it, so maybe it was 1/2, and I squared it, got 1/4. And I put this over, so cosine of t was 1/2. If we look at that with just numerical values in there, what would we do? We would maybe try to combine those. And because they're numerical, we could do that. Here, they're not so much numerical, so I don't know if I can do that. But eventually what I would do is I'd try to merge these two fractions into one fraction. Merge these two fractions into one fraction. If I'm going to merge two fractions into one fraction, I'm going to need a common denominator. So my common denominator, okay, my LCD here is cosine t. So I'll put a cosine t there. And then I'll put a cosine t here. Okay. Remember, because if I put this, and you might not see right away why I did that, if I put that denominator there, that just changed cosine t into 1. Well, I don't want to do that. It still has to be cosine t. So I need to multiply the top by it as well. It's like the idea if I take 1/2 and 3 and I want to add those together, well, I need a common denominator. Well, I can't just put a 2 there because that's no longer 3. I got to multiply that 2 up top as well. So that's what I did here with that cosine. So now, working that stuff out, that gives me cosine squared up top over cosine plus then sine squared over cosine That turns into cosine squared t plus sine squared t all over cosine t. Alright, so that's nice. What's cosine squared plus sine squared? It's 1. Cosine squared, or cosine t on the bottom. But what's 1 over cosine? 1 over cosine is secant. So what did we just find out? This is an alternative way of writing secant. Okay, and we can check this now. If you're going to check this, use this version of Desmos. But I'm typing, because this one has the secant function in it, or defined for it. So if I type that in, I just let my slider be t, and then I go secant of t. Do these two things evaluate? And the idea is that we've used identities, so they should evaluate the same way no matter what we use as our input. If we were to use x instead of t up here, hopefully that graph looks familiar because it is the same as our secant. So that's kind of the game we play here. We're going to try to do our substitutions with the trig identities and then try to simplify using our algebra skills. Okay, so I'll go through a couple more of these with you, and then I'll let you kind of get a jump on your work. So simplify the expression for cosine t tangent t. Again, rewrite everything in terms of sine and cosine. So I have 4 cosine of t times tangent of t is sine of t over cosine of t. Okay. So what happens here is that you've got now a cosine t up top. So if I were to multiply this out, you don't need to if you don't want to, but it would look this way. It's a fraction times a fraction. So I multiply straight across the top, straight across the bottom. And now you see that cosine t and that cosine t can cancel out, and you're left with just 4 sine of t. So 4 cosine t tangent t is the same thing as 4 sine t. Again, if you use Desmos, you could check it. It does pan out. So that's simply taking things. Those are examples where we just transfer things into sine and cosine. Okay. Well, what happens if they are already in terms of sine and cosine, such as this one here? If that's the case, the number one thing you want to look for is a GCF. And if I look here, I see a GCF. I see term 1 and term 2, and they both have a cosine in them. I'll factor a cosine out. To factor a cosine out of cosine cubed, it gives me cosine squared. Factor a cosine out of sine squared x cosine x, it's going to give me sine squared x. What is this? There's an identity right there. It's cosine x now times 1. So let's see if we make that connection here. If we type in cosine cubed, I don't know if, yeah. So here's the thing, if I go cosine squared x, Desmos knows that notation. If I want to go any other power for cosine or sine, or really any of these, I got to do this. It's going to pain in the butt, but that's how I type in cosine cubed. Plus then sine squared x cosine x. If I look at that, that looks exactly like that blue curve. So we have an alternative way of writing cosine. So if this were in an equation that we're working on later in chapter 7, it would be so much easier if we could make the algebraic connection that that is the same as cosine, just replace it. Makes my equation so much simpler to work with. All right. So this next one, but then one thing, guys, is because we know there's different ways of solving equations, there's different ways of simplifying, as long as I abide by my algebraic properties. You might do something differently than me here, but you might get to the same answer. Okay. In the past, I would, if we were in class, first period I would let class kind of guide the way we do that problem. And we get to second period, I let them guide it the way we do the second problem, or the same problem a second time, and we could compare our work from first period to second period, and they could be completely different. Okay, now you can maybe go through and say, okay, well, we did step 1, 2, and 3. They're actually independent steps, and in second period we did it in steps 2, and then 3, and then 1. You can do that, but my thought is if you're working with somebody or looking at my notes and thinking I've got to do it this way, there are alternative paths to these. Okay, so just be on the lookout for that. Okay, so this one, I see this. So sine. I see a number minus a number divided by another number. Well, if I'm going to do that, I want to merge those. I want to make sure that I've got one fraction here. Okay, so what I'm going to do is I'm going to write this as sine of theta minus 1 over sine of theta over cosine theta. Okay. Now, like I said, and I did that because I know cosecant is the reciprocal sine. I want to put things in terms of sine and cosine. I think that makes it easier for me. But now I see this. It's a fraction minus a fraction. What I need is a common denominator. So common denominator is going to be sine theta. So that first term will be sine squared theta over sine theta. If you do that division, it still gives you that term right there. Minus 1 over sine theta, and it's all over cosine of theta. Now I can combine. I can go sine squared theta minus 1 over sine theta all over cosine theta. Okay? So I just merged it into one fraction. Okay? Merge it into one fraction. Now what I can do, I see sine squared theta minus 1, and that rings a bell with me. Because if I have cosine squared theta plus sine squared theta equals 1, can I move that 1 over? So it gives me cosine squared theta plus sine squared theta minus 1 equals now 0. But let's move that cosine squared over. So does this make sense? That sine squared theta minus 1 is equal to the negative cosine squared theta. So I know that that top becomes cosine squared theta. I've got sine of theta, and now it's all over cosine theta. What I need us to understand is that that is a fraction. And the bottom one is also a fraction. Now the one on the bottom is a fraction because it can be written over 1. Well, how do I just normal values, normal numbers? If I had like 2/3 divided by 1/2, multiply by the reciprocal of that. So same thing. Let's take that one, multiply by the reciprocal. So we get 1 over cosine. And what happens here? My hope is that you see that you have a cosine times a cosine up top. So that one of those cosines there is going to cancel with that one. So then you have cosine times 1 on top, and you have sine times 1 on the bottom, and now cosine divided by sine, that is cotangent. So again, checking this, we have sine of, I'll just use x again, minus cosecant of x divided by cosine of x. This is why I like to use Desmos, is I can actually see kind of the math print, make sure I had things divided right. You saw that if I didn't have that one parenthesis, go back. If I didn't have that one set of parentheses, try to divide the cosecant by the cosine instead of the entire difference by the cosine. So that's just something to be aware of. And if I type in cotangent of x, then and we're seeing we've got something wrong here, right? Got something amiss. So what did I do? Sine squared minus 1. Oh, I know what I did. And this is nice because I can see. I mean, if I look at that green and purple one, I want them to be the same. They look like they are reflections of one another across the x-axis. If I reflect the purple one over the x-axis, it would become the green one, or vice versa. So that tells me I'm missing a negative, because reflecting across an x-axis is multiplying by a negative, and that's what happened right here. Remember when I took that there and I did all this work over here, it became negative cosine squared theta, but I didn't put that negative there. So then that should transfer to there, and then transfer to there. So then, don't know why I'm pulling my hair out. Then we've got a negative there. Now you can see that they are the same. So that is the nice thing about using Desmos or any other calculator to check these. Your TIA 384 is going to stink checking these because it doesn't have the cosecant or cotangent buttons on them. So you're going to type it cosecant n as 1 over sine. You'll type cotangent n as 1 over tangent. It just gets messy. But having something like this can allow you to quickly see maybe your mistakes or where you need to take something in the next step. So that's one version of the problems that we're going to see. Another one is what we call proving trigonometric identities. It's a similar way of simplifying. It's just going to give you an equation, and you're going to pick what you think to be the most complex side. There's no wrong answer to that. And you're going to try to simplify that side so that it looks like the other side. Okay? So if you read these guidelines, I'll let you kind of take these guidelines. You can pause it here and write those down. But let's just jump into examples here. Okay? So I want to start with this example, and I'm going to kind of remove this just to save a little bit of time here. If we were to graph these, they would be identical. Okay, so that's and they're going to be identical everywhere. So that's the proof. That's an identity graphically. If you chose a theta and plug the theta values in, okay, so choose an angle measurement and make sure it's the same everywhere. Evaluate the left-hand side, evaluate the right-hand side, you're going to find out they're the same. But what I want to do here is I want to choose a side that I think looks more complex. I think the left-hand side looks more complex. So what I'm going to do, this is just kind of the notation that you're going to see most of the time. You'll see people write LHS, stands for left-hand side, and I'm going to say that it is equal to cosine of theta times secant of theta minus cosine of theta. Okay? In this situation, I want to put everything in terms of cosine and sine. So I'm going to rewrite this as cosine theta times now 1 over cosine theta minus then cosine theta. And when I get to this point, when I got everything transferred into sine and cosine, what takes over is the algebra. You have to do what the algebra says here. And even if I look at the beginning, the algebra says to distribute. So that's what I'm going to do. Cosine theta times 1 over cosine theta. Those are reciprocal, so it's going to give me 1. And then cosine times cosine gives me that. And now if we remember from this thing, sine squared theta plus cosine squared theta equals 1. If I go and subtract cosine from both sides, I get that. Which now I can make the substitution. 1 minus cosine squared theta is equal to sine squared theta, which is what we wanted to get to. We wanted to start with the left-hand side and transform it so that it became the same as the right-hand side. So what we'll say then is that this is equal to RHS. So basically it shows, this organization of our work here shows that we started with the left-hand side, but we go through substitutions, and eventually it equates to the right-hand side. If I look at the next one, verify this identity. I think personally that the left-hand side looks. Okay, folks, the last video stopped abruptly because of my computer died. So we're going to example 6 here. I'm going to go left-hand side. I believe that's the most complex. It's cosine u over 1 minus sine u. There's probably a couple different things you can do here. my suggestion is when it's already in terms of sine and cosine, you can either merge this into one fraction, which is, common denominator, all that kind of stuff. But what I like to do with these types of problems is, and this is when everything is in terms of sine and cosine already, and essentially we have a difference on the bottom, is I want to multiply by 1. I multiply a convenient value of 1. Okay, I would hope you would see that 1 plus sine of u over 1 plus sine of u is still 1, so it's not going to change anything. But how does that and that relate? Hopefully, maybe it jogs your memory that those are conjugates. And when I multiply conjugates, O and I cancel out when I FOIL. So I'm going to go 1 times 1, and then sine u times sine u. That's going to be negative in this case, so that's nice right there. When I multiply the top, it's going to be cosine of u plus cosine u sine u. What happened on the bottom is nice because remember, sine squared plus cosine squared equals 1. If I subtract sine squared from both sides, I get cosine squared equals 1 minus sine squared. So this denominator actually is a identity that I can replace. I'm using u, so sorry I jumped to theta there. So that right there is the same thing as cosine squared. So then I have cosine of u plus then cosine of u sine u. Okay. In this case then, because it's a fraction, so if I had like 2 plus 3 over 5, that probably came from 2/5 plus 3/5. That's how I would rewrite it, as 2 plus 3 over 5. Well, this here is kind of starting on that side of the fraction and working our way back. If I have a sum up top, I can rewrite it as cosine u over cosine squared u, and then plus then cosine u sine u over cosine squared u. That's kind of the reverse of coming up with a common denominator. It's recognizing that you can split this in two separate fractions. Why would I do that? Well, what's cosine u or cosine squared u? Those are going to cancel. Leave me 1 over cosine u. Again, here I'll have a cosine u cancel, and it leaves me with sine u over cosine u. Well, what's 1 over cosine? Reciprocal is secant of u. Plus then this sine over cosine is tangent u, and that is your right hand side. I know, like at the onset, these things are going to maybe seem like overwhelming as you're taking notes right now. You're thinking, "What in the world? This is mind-boggling." Some of you, you're going to get it right away. This is going to be easy for you. Okay, those of you that struggle, there are endless videos on my website under section 7.1 of how to do this. Okay, these are things that you've got to practice at. If you're sitting at home, you've gone through these notes and you still don't get it, keep going through those additional videos, those additional resources. YouTube is your friend, especially in the situations that we're in right now, to fix these things, to get to understand what's going on here. Sometimes when you see problems like these, you have to work with both sides. Okay, so I might take the left-hand side, change it a little bit, maybe get stuck somewhere, and then take the right-hand side, change it a little bit, and hopefully the way I've changed them both, at some point they can line up. We can link them and say, yep, left-hand side at one stage is equal to the right-hand side at some other stage, and we're good to go. So hopefully this question here will demonstrate that. So I'm going to start with the left-hand side here. And again, I haven't worked these prior. I'm not 100% sure if things are going to work out here. We try something, see if anything makes sense. If it doesn't, we'll try something else. Okay. I see this, and I'm going to go ahead and maybe do this. 1 over cosine theta plus cosine theta over cosine theta. I can separate those. It's a sum over one denominator. Separate them. If I add those, I get back to that, right? What's 1 over cosine? It's secant. What's cosine over cosine? It's 1. Okay? Not sure what to do with that right now. Okay? But I got something in my mind because I'm seeing that tangent squared here. And if we go back up, it's one of our Pythagorean identities. If there is a tangent squared, tangent works with secant. So we know if tangent squared, I'll write this down here, tangent squared theta plus 1 was equal to secant squared theta. So here's what I'm going to take the right hand side. And I want to say, instead of tangent squared plus 1, I want to say that this numerator, I'll rewrite tangent squared. I'll just rewrite the whole thing. Tangent squared over secant theta minus 1. But tangent squared is the same thing as secant squared theta minus 1 right here. So I want to move that 1 over. This is what I get. Now, why'd I do that? Because I saw this here, and that made sense to me because I see this now as a difference of perfect squares. So it will factor this way. Secant squared minus 1 is that? Secant theta minus 1 times secant theta plus 1. And in the bottom then is secant theta minus 1. What's going to happen with that there and that there? They cancel. And it leaves you secant theta plus 1 when those cancel. Why is that nice? We just took the left-hand side and we were able to dwindle it down to that. Then we took the right-hand side and we were able to dwindle it down to that. So those two things are equal, they're the same. So that tells us the left-hand side and the right-hand side must be the same per when we started. So those two things must be equal, and that's the proof or the verifying that this is an identity. Now, so this is an identity. That means that whenever I see this, I could replace it with this thing here, or whenever I see this, I can replace it with that thing there. You don't see either of these enough for it to be a fundamental identity that we have to memorize. And that's kind of the game here. These are all identities, but you don't see this enough that you need to memorize that that is the same thing as sine squared theta. Okay, you're not going to see that enough to memorize or need to memorize that's the same thing as secant u plus tangent u. But they are identities that if you wanted to, you could memorize. I don't know if there's a maybe alternative way. Let's go with that one. Let's just see what happens here. This might lead to nothing. We had 1 plus cosine over cosine. So that was the left-hand side. Just trying to figure out what we did something earlier like this. We multiplied by the conjugate. Now I multiplied by the conjugate of the denominator previously, but it doesn't matter. I can still multiply by a conjugate here. So that's going to give me, so up top it's going to give me 1 minus cosine squared theta. On the bottom it gives me, I'm just going to leave it as cosine theta, 1 minus cosine theta at the moment. And that top then turns into sine squared theta. That's Pythagorean identity. And then cosine theta, 1 minus cosine theta. I don't know, maybe do this. Sine squared theta. Now I get cosine theta minus cosine squared theta. So it's distributed the bottom. I don't know. Let's go. Well, let's just leave that there for the moment. And let's just grab the right-hand side, which was tangent squared theta over secant minus 1. Tangent squared would be sine squared theta over cosine squared theta. Secant is 1 over cosine theta minus 1. I got a fraction divided by a fraction, but I don't like this one. So let's go ahead and rewrite that denominator as one fraction. So I'm going to have 1 over cosine theta minus cosine theta over cosine theta. That's just changing that -1 into a convenient version. So now I've got sine squared theta over cosine squared theta over, now it'd be 1 minus cosine theta over cosine theta. Okay, because now I can combine that, because those have a LCD now, I can combine those. Now I got a fraction divided by a fraction, so let's multiply by the reciprocal. So now it'd be cosine theta, and then 1 minus cosine theta. So when I do that, that cosine theta and that cosine theta there go away, and I'm left with sine squared theta. We have a cosine theta times 1 minus cosine theta, and looky there, that and that are the same. So that tells me those two things were the same. Again, completely different approach than what we did here, but it still works. Still gets us to the conclusion that we need, okay, to show that the left-hand side at some point using true algebra and true identities is equal to the right-hand side at some point using true identities and true algebra. You can check these. You can type them in your calculator. You can check, and that's the thing that I like about Desmos is I can, if I'm uncertain that I could have done that right there, I multiplied by the conjugate of the top, and it gave me this here. All I have to do is see, does that, if I graph that right there, and then graph that right there, does it generate the same graph? If it does, then this multiplication by the conjugate was 100% acceptable. And those are just little things that I think that we don't necessarily teach deliberately in a trig class, but it's something that is a byproduct of wanting to know if I'm doing something correct. Grabbing that calculator, messing around with it, see if I make those connections, and it will then inherently just build your algebra skills for you, and hopefully refine them to a point where eventually you don't need the calculator. I'm going to post an assignment over 7.1 on WebAssign. The next time I post something, which will be 2 days from now, or Friday, I guess, we will go over these addition and subtraction formulas. Okay, and these are a little bit. I think you'll prefer these over maybe what we're doing here. Okay, but this stuff here that we're doing is going to be something that is just present in a lot of the problems that we move on throughout the year with. Working with identities and simplifying things is much like how often LCDs and combining like terms and dividing fractions by fractions occurs inside algebra. Simplifying trigonometric expressions and identities and using identities occurs a lot through our trig relationships later on. So hopefully this is a benefit to you. If, like I said, if you are struggling with this, you don't need, obviously we only did 7 examples there. If you need more examples, okay, chapter 7 here, 7.1, trig identities. You can go through a load of notes here, okay? Each one of these is probably about 40 minutes long. It's a class session. That was last year's. This was the year before. These are all examples of somebody else doing similar things, okay? You have a lot of resources here. Please use them to develop some skills here. These, I believe, they might be different than these. I think they are. So use those, please, and contact me if you have any issues and concerns.